the context of the presentation. I'm going to talk first a little bit about the introduction, the motivation for the work, the proposed solution, the method, the materials, and the methods that the data we use to test the method, the results, some results, conclusion, and references. Okay, so if you have a sample when you apply out-of-plane loading, you apply out-of-plane loading, it's going to show out-of-plane displacements, of course, right? And so the idea is that I was working a few years ago, working with this data, and we were using an over-deterministic method for modes 1 and 2, and I realized that some samples also exhibited showing mode 3 displacements. And we didn't have the same method, the same over-deterministic method to calculate the SIFs in mode 3. So at the end, we use a simplified technique, COD, configurator. But it made me think that we need a more robust method to calculate K3 from displacement fields using the full field displacement fields given by the digital mass correlation technique. So in these samples, I'm going to show you how, for example, the samples exhibit mode displacement in mode 1, sorry, mode 2, parallel to the crack in mode 1, perpendicular to the crack, and in mode 3, out-of-plane displacement. Okay? And we all know that the DIC technique already gives you separated fields, displacement fields. Oops. Okay. So what happens if we don't include mode 3 in a calculation? We have a mixed mode load. Well, according to some theoretical models for equivalent K, for example, the Tanaka or the Hook models, the equivalent sensitivity factor will be lower, right? In both cases, the duration is linear, right? Here you have the square of 4 is 2, and the square of K3 squared is K3 divided by 2 will give you a linear relation. The same here with Tanaka is a little slightly different because it includes the Poisson ratio. So it will give you a lower intensity factor. Also for propagation, it will give you an error. Here, this is the Richard model. It's a phenomenological model. That's several of them. This one, I chose this one because it's really simple to see the difference. If you leave out K3, it will give you a wrong estimate for propagation. So basically, what I'm trying to answer here is how can one use the full DIC displacement fields in the out-of-plane direction to calculate a SIF in mode 3. So the solution I propose comes from is based on the Williams solution for displacement fields in mode 3. This is here have the crack. The coordinate system is pointed at the crack location, with the x-axis aligned with the crack direction growth. And for example, if you have 2 points A and B with displacements measured, U in the parallel to crack direction, B perpendicular, and W out of plane. Of course, you can see that points opposite to the crack show different signs and displacements. And this is the solution proposed by Williams, where W is the displacement out of plane, G is the torsional modulus, the shear modulus, R and theta are coordinates, important coordinates, and N is the number of terms using expansion, and C sub N is the term related to K3. Right? The first term, the series will be related to K3. So this equation 1 can be expressed as this equation 2, which is the same, just put in a different form, where again C sub 1 is C sub N is related to K3, P sub N is a matrix of form functions, and N, capital N, is the number of terms the number of measure points. TZ is the displacement in the rigid body displacement, sorry, and R theta n is the rotation in the out of plane displacement. So that equation can also be arranged in a matrix form. We're going from a continuous equation to a discrete form. So here H equal to B times delta, where H is the concatenated vector of displacement W, already mentioned by the technique. Delta 3 is the vector of non-coefficients, which is going to be related to K3 for a number of n measured data points. And B3 is the vector of terms in the form function described here in this equation, right? And expanded here. Okay, so we can see that we have an over-deterministic method over this problem, which can be solved by the least square method using the pseudo-matrix form shown here in equation 6. So we're going to implement this equation 3, in the following slides. So to test the method, I was fortunate to have some data, some samples. These samples were thin tubes made out of S230 steel. It's a 0.2 stainless steel according to European standard, 2.0 millimeter thick. The tests were subjected to in a biaxial machine to in phase tension and torsion, 90 degrees out of phase tension and torsion, and 45 degrees out of phase tension and torsion. In all cases, the load ratio, the axial and the torsional ratio was -1, was fully inverted. And in 3 cases, with more or less degree, all samples show the 3 displacement fields. It's also important that the fields were recorded using the 3D big software from correlated solutions. And so the data exported from 3D big is basically an array of matrices. These matrices show the 6 matrices for data in pixels, 6 matrices for data in millimeters, which are 3 for position, 3 for displacement. And so basically an array n times q, where m and n is the resolution of the picture, and q is the number of matrices you have. Some results here of the samples. Here, for example, is the sample with the 45 degrees out of phase loading. You have the crack here. The green star in 3 cases is the crack tip location. The yellow square areas is the data we use for the over-deterministic method. And also the red dots are the points, the data for the simplified COD method. Here we have 2 displays for opposite to crack points, so you can calculate the sensitivity factor in a really simple way. So we're going to compare equation 3 with this method of equation 7. If one, this will be the steps done, read the matrices, read the order, convert them into vectors, enter the crack location. I'm not going to talk about this because it's a whole different story and completely out of scope. Apply equation 3, solve with the pseudo matrix, and show results. So to compare, we compare with the COD method, that it would be the standard if we don't have a crack opening gauge to measure the opening and compare to sensitivity factors. We also computed SIFs in mode 1 and 2 to verify that the area of inspection U, the data, was all right. See? And also to keep the methods consistent, we use the same crack tip location for both methods, because for the Williams series, both that's a key factor. Some results here. This is for the sample with the in phase tension and torsion. We see for example, this is in all the graphics. The horizontal axis is actual load, and the vertical axis is the sensitivity factor. This also the same range, mode 1, mode 2, mode 3. Here, for example, we see that both methods agree, except here for this part where the load is negative. The COD shows the coordinating curve, the over-deterministic doesn't. But for a negative load, it doesn't make sense to have a K1 because the crack is closed, so K1 doesn't exist. For mode 2, we almost agree. The glitch. Always the glitch. That is kind of thing. For mode 2, we have also an agreement for shape and values, pretty much. For mode 3, in this case, the LSN shows slightly larger values than the CO2. This is more interesting because it's going to start showing examples with no proportional loading. This is 90 degrees out of phase, 90 degrees out of phase station torsion. For mode 1, there is pretty much agreement between in shape and values. It even shows that machine with the test slightly overpeak here, overshooting for the initial load. Even agrees with both of them, like I said, in shape and values. For mode 2, COD shows slightly larger value than the over-deterministic method, but both agree in shape. For mode 3 is basically the same too. And also something interesting here is that like both agree that showing that modes 2 and 3 exhibit a flat curve for once the load is open, because you have to remember here the loading here 90 degrees. So one is maximum, the other one is minimum. So in this case, the crack stayed completely slide completely, and you can see that the different sides, different sides. This one is 45 degrees out of tension torsion. In here, this one we also check the influence of the expansion terms on the model, and we basically found that there was no much difference, no much than the over-deterministic method. Okay. And the method allows to capture the full extent of the SIF and the SIF range, including nonlinear effects such as plasticity, crack flank, interlocking, porosity. We also here show that the K1 does not meet physical sense, like I told you before, right? Here you have to account the sign of the displacement. Remembering that for sliding, the sign means only that sliding is a relative sliding. Okay, and that sliding would most likely produce smoothing the crack. And here also, I'm trying to show, trying to draw an analogy between displacements and stress intensity factors. There's some indications in literature doing that before for mode 1 and 2. Here, I'm trying to extend it to mode 3. This is an analogy that we do with vectors. If you have the full displacement here, and one of the orthogonal components change, if this one stays fixed, the full vector, but one component changes, the other component will change as well to keep the vector constant. So that would mean that the angle alpha, which is the in-plane crack kinking angle, will change, and in case delta 3 changes, the out-of-phase angle also will change. In conclusion, presented a method to establish K3 from displacement data. The method was applied to 3 tubes subjected to different combination of axial and torsional loads in phase and out of phase. And the results were compared with the COD method, agreeing for the most part. And also the proposed method seems to capture the plasticity and provides also less noisy results. Also, because the samples were curved, and we use a radius as a straight line, approximately the radius, the distance in a straight line, and so that would cause an error. We kept that error, trying to keep that error closed by using the data area as close as possible to the crack tip, to minimize the curvature error. I want to thank you, Professor Borgmal, and Amsterdam for facilitating the investigative data and the lab at the Laboratory for Photomechanical Cook Rio, where I did the analysis. These are the references, and after coffee, you are welcome to ask questions.